Welcome to this lecture on output equation of single phase transformers. The output equation relates the kVA of a transformer, that means the power of a transformer in kVA, with the main dimensions of the transformer. That means it helps to define the main dimensions of the transformer. Let capital Q be the output in kVA, phi m be the maximum flux in Weber, Bm be the maximum flux density in Weber per meter square, and delta be the current density in the primary and secondary conductors. And let Ai be the net core area in meter square or net iron area of core in meter square. That is equal to stacking factor into AGI, that is Ki into AGI. And let capital AC be the area of copper in the window. It is total area of cross section of conductors, copper conductors in the window in meter square. AW be the area of window in meter square, and KW be the window space factor. And let TP and TS be the number of turns in primary and secondary windings. IP and IS be the currents in primary and secondary windings. VP and VS be the terminal voltage primary and secondary windings. And AP and AS be the area of conductors of primary and secondary windings. Now let's derive the output equation. Output equation of a single phase transformer. The EMF induced per turn in a transformer winding with T turns, number of turns is represented by capital T. T turns and excited by a source having a frequency of F Hertz is EMF per turn ET is equal to capital E divided by capital T. Capital E is the EMF induced and now T is the number of turns, EMF per turn. This is applicable for primary as well as secondary. EMF per turn is equal to 4.44 F phi m. That is equation number 1. Then the total area, copper area in the window. Total copper area means the total area of cross section of copper conductors in the window. That is AC is equal to copper area of primary winding plus copper area of secondary winding. That means in a particular window there will be primary conductors as well as secondary conductors. So total area of primary as well as secondary conductors will give you the total copper area in the window. That means AC is equal to primary turns into area of primary conductors plus secondary turns into area of secondary conductors. Then we'll denote these values or denote these terms in using the symbols or using the notations. Primary turns TP into primary conductor area AP plus TS, secondary number of turns, AS, area cross section of secondary conductor. That is equation number 2. Let delta be the current density in both primary and secondary conductors. So delta is equal to IP by AP. IP is the current in primary conductor, AP is the area cross section of primary conductor. That is equal to current in secondary divided by area cross section of secondary conductor. That is delta. Both are equal. From the equation for delta, we can write AP is equal to IP by delta and AS is equal to IS by delta. Therefore, the total conductor area in the window, that is AC, can be rewritten as TP into, here we had written AP, TP AP plus TSAS. That was the equation. So instead of AP, we are writing IP by delta. And instead of AS, we are writing IS by delta from these two equations. That is equal to TPIP plus TSIS all divided by delta. Neglecting the magnetizing MMF, the ratio of IP by IS is equal to Ts by Tp. This equation is familiar to us. So we can write the equation for AC as 2 into number of turns into current Ti divided by delta is equal to 2 into 80. 80 means the MMF. Number of turns into current will give you the MMF for primary or secondary. So 80 is the MMF. 2 into MMF divided by delta. That is equation number 4. Now the window space factor. We had already defined a term called window space factor, that is KW, which is the ratio of conductor area in window divided by total area of window. Conductor area, copper conductor area in the window divided by total area of the window. That is equal to AC by AW. So AC can be written as KW into AW. So we have two equations for AC, that is equation number 4 and equation number 5. We are equating these two representations. So we can compare these two equations and we can write that like this: 280 by delta is equal to KW AW. From this we can write the equation for AT, that is AT is equal to delta KW AW by 2. AT is the product of current and number of turns. Now we are going to write the output equation. It is rating of a single phase transformer in kVA. That is Q is equal to Vp Ip into 10 raised to minus 3, where Vp and Ip are the primary voltage and current. 10 raised to minus 3 is for representing this in kVA. So let's assume that the primary terminal voltage is equal to the EMF induced in the primary voltage. Vp is equal to Ep. So Ep is equal to EMF per turn into number of turns in primary. That is Et into Tp. Now the equation for power Q is equal to Vp Ip into 10 raised to minus 3. That is equal to, instead of Vp we can substitute Ep. So Ep is Et Tp. So Et into Tp into Ip into 10 raised to minus 3. Here Tp into Ip means MMF. T into I, that is MMF or AT. We have already derived the expression for AT. So we can substitute for TPIP here. So ET is 4.44 FIM and TPIP is 8 and AT is KW delta by 2. By rearranging these terms, we can get the expression as Q is equal to 2.22 FIM KW delta into 10 raised to minus 3. And we can write the value of phi-m as Bm into Ai, where Bm is the maximum flux density and Ai is the net ion area of core. Then the equation becomes Q is equal to 2.22 F Bm Ai Kw Aw delta into 10 raised to minus 3. So this is the final equation or final expression of output equation of a single phase transformer. Thank you.